So today we're going to study the induced electric field. Okay, so let's see, in some region we have some magnetic field, and this magnetic field is going onto the page. So I put here plus. This is the back of the arrow. So we have here the pluses. You see, these are the magnetic field going in onto the page. So in this region here, you have this magnetic field. If the magnetic field, this is the B field. If the magnetic field is constant, nothing will happen. You don't have any electric field generated because the magnetic field is constant. Okay? It doesn't change. But let's see if this magnetic field somehow is changing, is increasing. Let's see, the B field is increasing. What will happen? If the B field increases, what's going to happen? You're going to generate an electric field. How are you going to generate the electric field? Before I explain how we're going to generate this electric field, we need to write this formula here for this is Faraday's law in an integral form. So I put here the integral of, this is the electric field, dot, I put here the distance, ds, is equal to minus the change of the flux, the magnetic flux, with respect to time. If you remember from last time we did this, we put here E, which is the voltage, is equal to minus d phi over dt. You can see here that the electric field times the distance, that's the voltage. So this is a voltage. So what's going to happen when you when you have a changed magnetic field here, you're going to generate when you're going to generate an electric field. So this electric field that's going to be generated will look like this. Will actually go like that. This line here. There are a bunch of circular lines, but we look at just one of them. So you have an electric field line that go like this, circle like that. Now, we need to know the direction of this electric field. Is it going counterclockwise or clockwise? To know that is, we need to understand one thing. If the magnetic field is increasing, due to Lenz's law, you're going to have a current that's going to generate a magnetic field that's going to oppose this magnetic field that's increasing. So we're going to have a magnetic field due to this loop here that's going to come out like that. This is the head of the arrow. The arrow is coming at us. So we know that the current goes from positive to negative, and we also know that the electric field goes from positive to negative. If you have, for example, here two plates, this is negative, this is positive, the electric goes like that. So what's going to happen? The current that's going to oppose these, that's going to generate a magnetic field, that's going to oppose this blue magnetic field, has to go in this direction, like that. Now why? We use this Lenz's law. So I grab the wire, use my thumb, and look at my fingers here in the middle, they're coming out. So the current has to go this way. So now what's so interesting, this is an electric field. So the electric field actually will be circling. So you have electric field here circling around like that. Along this ds, you can call this distance here ds. So the electric field is going along the s. So now when you sum, here we put here the sum, this is the integral, sum of the electric field along the s. We sum it. You get the voltage. So it's like a voltage gets created in this location here to generate this electric field. So a changing magnetic field creates an electric field. So we have an electric field here in space due to the changing magnetic field. Now, this magnetic field, if it's constant, you won't see any electric field. And once you start increasing it, you're going to have a magnetic field, you're going to have an electric field that's going counterclockwise. And let's see if you decrease in the magnetic field. If you decrease the magnetic field, the electric field will go clockwise. If it goes clockwise, it will try to put the magnetic field that you lost. You see, when you decrease the magnetic field here, you lose in magnetic field. So this electric field, or this current, we can say we have like some current is generating a magnetic field to go in the same direction as the old magnetic field to compensate for it, because the old magnetic field is getting weaker if we decrease the original magnetic field. But remember here, this is space. We don't have a wire. So what you have here is just an electric field circling. So you don't just have one line. You have a bunch of lines. You have another one here, another one here. There are a bunch of them, these electric field lines circling as you increase this magnetic field. So before, when we have just magnetic field constant, there was no electric field in space at all. And now we just put a magnetic field and we increase it, and then we get electric field in space. So the magnetic field, a change in magnetic field, creates an electric field. Now, if, this is what's so interesting, if you put a current, if you put some wire, this is a wire here. Remember, before we don't have any wire, we just have space. When we have space, we just have electric field. But now if you put a wire here, you're going to have that electric field generated, okay? And that electric field is going to, in the wire, is going to make a current, push a current. And then you have a current. Now, the current will be going like that. So if you put a wire or a loop, some wire, you're going to generate a current by changing the magnetic field. If you don't have a wire, you're going to have an electric field. So this electric field here is the one that actually pushes the electron to go around. The electrons, they're going to go the opposite way of the direction of the current. So if you put a wire, those electrons that's inside the wire will feel that electric field and they will start moving like this clockwise. If you take off the wire, you just have electric field by itself going like that, circling. So this is an induced, created electric field in space due to a changing magnetic field. Okay? So this is Faraday's law. Faraday's law, it says, I can generate the electric field in space. If you put a wire, I'll generate a current in that wire. So a change in magnetic field generates electric field in space, or a current in a wire. Now, we need to understand this loop here that we have in the integral. Now, the electric field is going around. So the reason they have this circle, it means you have to sum all around the loop here, this contour. You keep summing the electric field dot ds, electric field dot ds, electric field dot ds, summing. When you sum all of this, you're going to get the voltage across that wire, if we have a wire, or you get these change in flux here. And that's the induced electric field.